Okay, right. Start curve, surface, and wraps. Okay, so I hope you guys have already created at least some know how to create some curve in either in Rhino or in Grasshopper, right? So I'm not going to the basic of like curves in Rhino. I'm just like talking what is the parametric curve and how you do it from script. All right, let's get straight to the point. So usually a freeform curve in Rhino or any freeform curve modeling software for that matter, not just Rhino, but also PowerPoint also allows you to do freeform curve, right? Freeform curves are created using a bunch of control points, and guess what? Control points are just point 3D objects inside Python. All right, so let's try out this example. We're going to input a bunch of points, and then we're going to use the single command. So let's set up a simple Grasshopper, simple Python component. Yes. Yes, it's has been recording. Yeah, it is. Okay. All right, a list of points, and the output is just called an O curve, output curve, right? Alright, give it a few points. Today we have only 28 slides, so relatively fewer than the previous days. Okay, so let's try out the command. If you finish preparing the component, you can either type in a copy and paste, but let me explain it first before you try. So, this is the command that creates the curve, okay? So, or the functions. From now, you know what a function is, so I will call it functions, okay? This is the function. This is a function that live inside the class curve, okay, or the data type curve. So that's why we have to say the data type name first or the class name first, okay? And this class name is defined within the RG library, right? So RG curve and then create interpolate curve. This one take in two parameters. The first one is obviously the list of control points. The second one is an integer, and it might not be hard to get what that integer is. So this is the degree of the curve or the smoothness of the curve, right? We will talk about the degree of the curve a little bit in the following slides, all right? So it will give you an interpolated curve that passes through all of the control points that has degree 3, all right? So let's try that. Okay, so this command exactly gives you the same functionality as this component called interpolate curve. Or just interpolate. So this one take in a bunch of vertices and the degree, which is 3 by default. Okay, sorry, this should go here. All right. No, this one is degree 3. No, they're not the same, so I lied to you. Actually, not intentionally. So why they are different? Maybe this is degree. Oh, so they are degree 4. Wait, what? Okay, so Grasshopper lied to you, not me. So this is to say degree 3, but here I input degree 4 and they look the same. Okay, that's odd. That's really odd. Okay, so in mathematics of curve, there is two concepts called the degree and the order. And the order is usually just degree plus 1. So I think what it means here is not a degree, but the order of the curve. That's why it's 4. Okay, so they're just two different names, but they always different by 1. So that's my theory, really. Anyway, So what is about interpolate curve? So the interpolate curve always, I can also, sorry, I can, before I talk about what interpolate curve, I can also do interpolate curve in the main Rhino user interface, right? This is the interpolate curve. So the interpolate curve always pass through the control points fully, okay? So that's why the name interpolate. Because let's say that you have a bunch of data points. Okay, this point, let's say that you scan a rod of bamboo or like a 3D rod of bamboo, right? And you get a bunch of points. You put it in a computer and you ask the computer, hey, from this point, can you reconstruct the original curve? Then you are doing interpolation, right? From a bunch of control points, you want to put a smooth curve through all of those, so you're doing interpolation. That is why we call this kind of interpolation curve. All right. However, that is not kind of the standard kind of curve in Rhino. Okay, so before I come back to the Python syntax and the Rhino common documentation to this one for that particular function, let's just talk about curve a little bit. So the one we just create is interpolated curve. So it's a curve that guarantees to pass through all of the control points. Now technically these in this case are not called control points, they are called interpolation points. Okay, they just input point, but they're not called control points. All right, now the other kind of curve is called the approximate curve. That's the real name in kind of common graphics, but in Rhino user interface they call it control point curve. So this curve is created by the user, us specifying a bunch of control points, okay, and then Rhino will create a curve that only guaranteed to pass through the first and the last control points, and influenced by the other control points, but usually not pass through it. Okay, and that is this type of curve here. So the standard control points curve. So the first control point, the second control point, third, fourth, last. Okay, so it's only guaranteed to pass through the first and the last one. Or if you count from zero, and this is the fourth one. Okay, but the middle one influences the shape of the curve. Okay, but it does not pass through. Okay, so let's see how we can create that approximate curve or this control points curve in Python first before I explain the advantage and disadvantage of these two types of curve. All right, so if we go back here in the Python script, all right. Now we're gonna change this to, instead of create control points curve, we're gonna say create. Instead of say create interpolated curve, we're gonna say create control points curve. And this one we also take in a list of points, but these points will be interpreted as control points, not interpolation points anymore. All right, and then the degree. Okay, what is the error now? Create control point curve. I'm missing the word curve in the name. All right. Okay, and now we have the curve that pass through the first and the last control points, but not everything. All right, and if you move the input control point, yeah, things gonna change accordingly. And just for comparison, I'm gonna do the curve, a NURBS curve. Okay, so this one will give you exact same result. NURBS curve degree 3. Okay, so now the degree actually work. So this is the one I create using Python. This is the one I create using the build component. They look exactly the same. All right. So why are they? So which one is more advantageous? So looking at these two. So now behind the scenes, this is the main thing, right? This is how Rhino manage or control the curve. Okay, by a bunch of control points. When we create this curve, what happens is that at the moment of creations, Rhino will guess the control points for you automatically. Okay, so this is what happened. So I'm gonna do the interpolate curve. Okay, so they clearly pass through the interpolation curve, but once I finish creating the curve, I'm gonna lose access to those interpolation curve. They will be converted to control points curve, which lies outside. Okay, so this kind of do a backward problem, like how I can so how Rhino can, when Rhino solves a small problem behind the scene, how I generate control point curve automatically to get a curve that exactly pass through the user interpolation curve. But the interpolation point is only valid at the motion of creations, right? If you want to kind of move the control point somewhere, you have to do it again. Now, of course, if you do from Python script, when you move the interpolation curve, the script will run again. So, but like in the main user interface, you lose those interpolation curve, right? So the control points curve is the official type of curve. But looking at these two, you might think that this one seems to be more intuitive to work with, right? So why doesn't Rhino use this one? I mean, having a curve passing through all of the interpolation curve is more intuitive than not passing through all of the control points, right? But the de facto or the standard kind of modeling curve in most modeling software, even PowerPoint or Microsoft Word, are this curve, not this one. Now the reason is because even though the interpolation curve seems more intuitive, it's actually harder to control. Let me demonstrate. So this is the standard. So imagine that you're a designer and you try to shape something with this one. It's actually much more predictable. Okay, it doesn't change that drastically. But if I change this to an interpolation curve, create interpolated curve. Okay, this one seems intuitive at first until you start changing it. And you see the influence is much stronger. I change something right here, and you see this thing kind of wiggle a bit counterintuitively. It's kind of annoying. And then if I come really close, this thing starts to become like twisting. Okay, so it's not that intuitive for fine modeling. So that's why, especially when you do car modeling, right? You don't want to like, or you imagine you do car modeling or any product modeling, and you wiggle a little bit of this part of the car, and somehow the other parts start moving unexpectedly. It's very annoying. All right. Now another thing with another advantage of the control points curve, let me draw it out here, is that if you look at the control point, so this is the this one is changing a bit. It's a bit dim to see. You see the line connecting the first control point to the second control point. This line always happens to be tangent to the curve. Same with the last segment. Okay. Let me move it here. See, it's always tangent, which means that if you have another curve, and if you want to make that curve join smoothly, all you need to do is to make sure that the tangents line up. If I draw another curve, one, and make sure that the tangents of the second curve line up. Okay. So if you see the tangent here and the tangent here, they line up, and here I will have a smooth join. Okay, I have to be a little bit more refined, but the direction is kind of yeah, you see. So but with the interpolation curve, you don't have that tangent guideline to make sure that everything is smoothly. And of course, when you do it by hand, you need some snapping tool to make sure it's fine. But if you do it Python, right, you can pre-generate these control points in a algorithmic manner, make sure that they line up, right? Okay. All right, so that is some kind of NURBS curve 101, more or less. All right, about the degree of the curve. Okay, so one thing I haven't explained is the degree of the curve, right? So for now, intuitively, the higher the degree of the curve, the smoother the curve will be. That is true for both interpolated curve and control point curve, because remember, behind the scene, interpolated curve is just control points curve. If I increase to number 4, for interpolated curve, you always need an odd number. Degree is always an odd number. So 5. Okay, so go from 3 to, let's be back to 3. Okay, 5 is Now let's do it with control point curve. So create control point curve. So degree 1 is the lowest degree. It will just be straight lines, it's not curve, right? Because degree 1 is just a linear function. If you remember from your mathematics at high school, the linear function is just straight lines. Degree 2 is the lowest one that will give you a smooth curve. Okay, they're fairly smooth, but you know, usually the default value is free. So when you model a curve, either in a Grasshopper, either in a main Rhino user interface or using the Grasshopper component, the default degree is always free. I will explain why it is free rather than 2 at the moment. Like 2 is clearly already smooth, right? But why sometimes it's free by default. Okay, and the higher I go, the smoother. Okay. All right. So let's look. So that is the about curve in general. Now let's look back at the Python side a little bit, like this Python command. So let's look at the Rhino command documentations. I'm gonna open it in a second. Rhino common curve class. Yes. Okay, so the curve data type, okay, it's represented by a class, that's why curve class, but it's just a data type. And here, inside this class, there is a bunch of functions or methods. Now remember, a function defined for a data type requires you to have a variable of data type first. For example, you must have a variable called myCurve. Only then you can say myCurve dot, and then myCurve dot, for example, closest point, right? So those are for the standard data type method. For those that is marked with the S letter, they are static methods. Static means that they are not associated to a specific curve object. They associate with the curve data type, okay? Not an object, which means that when you want to invoke this function, you don't need an existing curve object. You just need to call the. You just need to use the name of the data type, which is curve, right? So that's why we say rg.curve, capital C, and then dot create interpolate curve. This is a static function, so we invoke it on the data type name, and it makes sense. These functions create a brand new curve from scratch. That's why it doesn't make sense that. It doesn't require a pre-existing curve to call with, right? If you want to do dot distance 2, we need an existing point like my point dot distance 2, because that function requires an existence of a point first, right? But this function create curve is clearly doesn't require existence of a curve, so it makes sense that this is a static function. Okay, so when you look at the documentation, whenever you see the word static, it means that you can invoke it directly from the class name. All right, that's true from C# and that's true for in Python as well. This documentation is again written in the Python in the C# language, but there's like an almost one-to-one translation between C# and Python. All right, so create control point curve. Let's look at the documentation again. All right, so the name, the input list. This one has only one entry. The name of the input is points, but again, the name is not important. The name is just like a human, it can be anything. It's a data type that matters. So IEnumerable point3d is just a fancy name. It means a list of point3d object. That was we gave it to the command, right? And then the return object. Remember that yesterday what we did the other day. Any functions can optionally return object. This function create a curve, so of course it return an object of type curve. Okay, so it will return an object. This object doesn't have a name; it just have a data type, right? It's called curve, and we store this curve in this Python variable, which just happen to be the output. All right, so. Alright, so the return value has type curve, okay? So it is specified here, but it's also specified here. So in Python, this is what a function header, or like the title of function look like. It consists of the return type, meaning the data type of the return data, then the name of the functions, and then bracket the list of inputs. Now these two keywords in front, the public just completely ignore it. It doesn't exist in Python. It's only relevant to C#. But static, so the function that marked with the keyword static, I already explained what it means. But most of the function normally don't have this word static, which means that it's an object function, which means that you need an object of type curve first in order to invoke it. All right, what other information we need? Yeah, that's it really. Okay, so again, so from now, whenever I see a pretty fancy or complex function, I will keep refer to the documentation, so to help you get used to it. Okay, it takes some time to like fully feel comfortable navigating the documentations, especially when it's written in a different languages. Okay, so now let's come back to curve. Okay, let's again pause the programming a little bit. So about curve 101. So higher curve degree gives smoother curve. That's one you know. Higher curve means each point of the curve is okay. This one I hopefully you know. So degree free is that when you so each point on the curve. So like a curve is a collection of points, right? And each point there is a mathematical formula behind them to generate the XYZ coordinate of that point. Now for a point of degree free, then each point on the curve, the math will give you the result. The XYZ coordinate of that point depends on free control points curve among the list of control points curve that you have. And the higher the degree, the more control points curve that it will use to average that position. That is why the higher the degree, the more control points curve will influence any one set of points. That's why it's smoother, because try to listen to or be influenced to try to be influenced by multiple control points at once. That's why the overall shape come out smoother. Okay, but the question is why degree free is usually the default value. Okay, so the answer is that the standard degree free usually the standard, because well the answer is that degree 1 is clearly just a line, right? So it's out of question. Then degree 2 is smooth but not smooth enough. And let me show what I mean by not smooth enough, and hopefully this will dispel this myth that an iPhone is just a round corner rectangle, because it's actually not. Okay, it's more sophisticated than a round corner rectangle. This is an example of a degree 2 curve. It is smooth but not smooth enough. Let me explain why. So if you look at the cross section, it's basically just a straight line, and then you stick a semicircle into it, right? And here is what happened when I mean by not smooth enough. So yeah, they look smooth, but if you display the directions, and now the direction of a surface is represented by the normal vector, right? Or just a little arrow that perpendicular to the surface. All right. So for this part, the direction is basically just point out upward. But for this semi circle, the direction is basically just a radial collection of ray, right? Now, if you look at the transitions, not the transition, but like the rate of change or the speed of change of the directions. Here the rate of change is 0, right? Here the rate, for this part, the rate of direction is constant. So for every the same amount that you walk along the curve, the direction changes by the fixed amount, okay? So no change, constant change, and that's constant change is not larger than 0. Then here's the thing: there is no transition between the 0, the no change zone to the change zone. Okay, so even though the position varies smoothly, the rate of change of direction is not smooth. Okay, and that can manifest itself in some kind of not very pleasant looking. Now, the normal, imagine this is a shiny surface, right? It's like a car surface where you put glossy paint in and it reflects the environment, right? Now, if you remember your physics math, the reflections is highly depends on the normal vector, right? If there is a discontinuity or a non-smoothness in the transition of the normal, then your reflect image gonna look kind of unsightly at that position as well. So that's why for product design, it's kind of undesirable. You want to, you don't want to put a circle right here. You want this to transition smoothly from, relatively from a 0 zone to like slow. So the rate of change will go from 0, but slowly increasing to a constant value, right? Now here's a render of that surface, and if you look at this one, you see the image distortion. You kind of almost see like a little seam here, even though there's no seam, right? When you render it, and this is like a car surface or a product surface. It's kind of look less appealing. All right, so if you go to degree 3, you kind of solve that issue. Now, in practice, for car design, for product design, people go to often to degree 5 in order to make it really smooth. So the iPhones look like a rectangle, and you just put in 4-quarter circle at the corner, right? Now it's actually not like that. Like when you do when you draw an iPhone in Illustrator, that's what how people model it. But like for the actual production of the iPhone, the 3D model is more sophisticated than just like taking a rectangle and put 4 semicircle, because then first it will not look as sexy and smooth as it used to look, and second, productions like because physically you have a CNC machine that trim out this part of the actual product or the frame of the iPhone, right? And also like later when you design something that's going to be milled by the robots, having the smoother the curve, the better it is for the machine to work, right? Because if you have a hard turn, the machine will have to fully stop before it can carry on, right? But if the smoother the surface, then the machine will like go very smoothly, and then it doesn't have to like do with stop. So it's actually also not just like visually better looking, but it's also good for productions. Okay, so all right. So that is about curve. Now let's do line curve. Okay, so this is where things can get slightly confusing. So we already know how to create line object or Python variable of type rg.line, right? Now we have line curve. So what's different between line and a line curve? Well, a line is strictly a mathematical line, with a start point and an end point. That's what we have been doing. The line curve is technically it's considered a curve, but it just happened to look like a line. Okay, so why these distinctions? Now visually they look the same, but behind the scene, inside the software and for programming, they are different. That's why we need to know the difference, right? So even though visually, when you display on the screen, there's no way to tell them apart. So line curve is considered a curve. Now there is something that we haven't learned yet, but I can talk briefly about. So when you talk about data type in programming, not just Python but in many programming language, there is a concept called the subtyping or derived type, which basically tell how the types of the data types are related to each other. Now, for example, line and point 3D, they are not related at all. They just like two different data types represent two different types of entities. Okay, but the data type curve has many child or sub data type. For example, line curve, NURBS curve, poly curve. Okay. Now, how do I know about relationship? Well, the documentation will tell you. Okay, but so the line curve is a subtype or a child type or a derived data type of the line curve. Now, what does it mean? Is that when you look at the functions and it asks you to give it an input of type curve, then when you use it, it is perfectly okay to give it an input of type line curve as well, because line curve is a subtype. Okay, so if a function if a function asks for a curve, you can give it not just a curve, but anything that is derived from a curve. All right, let me give you a real-life example. Let's say we have a type called human that represents all human on Earth, right? And there is a subtype called architects that represent, a small specified human, which is architects. Now, if a function that asks for a human, and if you have a human, you can input it as a function, which is fine. But if you have an object of type architect, that function will also accept an architect, because architect has all the full functionality of a human. So that functions, hopefully, so that function will happily accept the input architect, because it has all the information that it needs to work. All right. So if a function asks for a curve, because they expect the degree of the curve to work with internally, and if you give it a line curve, it will happily take it in. Okay. So that is the reason why we need to know about the concept of type and subtype. Now you will see in a moment. We're gonna create a loft surface using a function create loft. Now the loft surface, intuitively, what is the input? Input is a list of curve, right? A list of curve, and we will loft through, put a loft surface through the curve. Now, even though it's asked for a list of curve, you can give it a list of line curve as well, because a list of line curve will be interpreted as a list of curve. Okay, and a list or a mixed list of line curve, poly curve, and NURBS curve. Okay, because at the end of the day, they will all be converted to curve okay, when you input them to the functions. Okay, that is why we need to know about this concept of subtyping for now, but we will learn about it in a more formal manner in object-oriented programming. Okay. All right, so a line curve, this is how you do a line curve. Okay, rg.line curve. Okay, and then this line curve, not surprisingly, the constructor function will take in 2.3D. Now let's look at the documentation. How do we know that line curve is a subtype of curve? Okay, if I type line curve class here, it won't give me the result at the first hit because this search function is horrible. So normally I would search using Google. I would say Rhino common line curve class, and Google always give me the first hit, but not this horrible search functions. So, all right. So how do I know that line curve is a subtype? So it should specify here. So line curve is a subtype of curve, and the curve itself is a subtype of geometry base. You see how it's written, but forget about geometry base. We just start from here. All right. Now, in reverse, if you look at the class curve and you want to ask which type are my children, which type are derived from me, I can click on more, and yeah, it will take you to the end of the page actually. So you click more, it will take you to the footer of the page, and it will list out all of the derived type or subtypes or children type. So line curve, notch curve, poly curve. Notch curve is the most flexible one. Yes, line curve, arc curve, curve. Okay. All right. I almost never use curve procedure, so I'm not even sure what it means. All right. All right. So now we know how to create a curve. Let's see what kind of operation we can do on a curve. All right. So any class curve has so compared to point 3D and line, if you look at the definition, the documentation for the class curve, they have a lot of properties and they have a lot of methods, right? Let's look at some useful one. Point at MOP. All right, the function point at, this is not a static function, so which means that you must have a curve first, right? And then imagine you start a curve in the variable called myCurve. Then you say myCurve dot point at. Okay, and let's see what parameter it takes in. Well, it just takes in a number that specifies the curve parameter, and then it will give you a point 3D object at that position on the curve. So in case you don't know what a curve parameter is, so in parametric curve modeling, whenever you have a curve, then each point on the curve is addressed or specified by a single number. So usually by convention the number starts from 0.0 and it's decreasing and usually stop at 1.0. And if you specify 0.5 and 0.5, will give you a point somewhere here. Okay, so basically each point uniquely corresponding to a number, and if you have a number, it will give you a unique point on the curve, right? You know how to do that using the point at component, or I think it's called evaluate curve. I think. What's the name of that component? Evaluate curve. Evaluate curve. Yes. Okay. But now, if you want to do it in Python, imagine you have a curve. So this one will give you a curve, right? Okay, so let me make another output, and I will say O point. Okay, I will have the curve here, but now let's store this curve into curve. Okay, into a variable, and then separates the output out. Okay. Okay, so I create a temporary variable to hold it. And again, many of you will ask why I separate the temporary variable from the output. It's just a good practice, especially later on when you do the timer. You don't want to use the output variable as a variable for computation inside the script. It can like cause confusion. So, all right. So curve dot point at. Okay, it will give me, and it will ask for a number. So I will put in, let's say 0.5, okay, and this will give me a point, okay. I will call it point on curve, okay. Okay, and I have to output this point, so O point equal to point on curve. Okay, I should see a point somewhere here. All right, so you need more time or shall I move on? Okay, so 0.5 will give you this one, at least with my example. You might have different result on your screen. So by default, this curve is usually not reparameterized. So the okay, if you don't know what reparameterization is, let me give. I'm gonna spend 1 minute to explain on that. So as I said, every point on the curve can be described uniquely by a number, or say, and that number starts from 0, and usually, actually, it starts quite arbitrary. It can start from a negative 10.5 up to 7.8, right? And that range we call the curve a domain, okay? Now, for convenience, usually we're gonna map this range to 0.0 to 1.0 because it's more easy to work with. So, you know, every curve, no matter how long or how complex it is, we use the reparameterized versions or the percentage version where, you know, the starting point is like 0% and the stop is like 100%. And if I give it like the point 0.5 or 50%, it should give me a point somewhere along the curve, right? So when we create, now if you have a curve, I think if you have a curve in a standard Grasshopper component, you can right-click and reparameterize it using the Grasshopper user interface, right? But in Python script, you can also do it. So after this line, I create a curve, right? Now this curve is not reparameterized yet. So let reparameterize it by set the domain to the range 0 and 1. So I will say curve dot. Okay, this is where I have to look up the documentation because I can't remember the name of that. Properties, I think it's called either interval or domain. Let's say, yeah. So domain. All right. So the domain is domain equal to. Okay. So the domain is a property, and the value that we put in the domain is a value that has the data type interval. So it's not a single number, but so the data type is not a float number, but an interval. Okay, so why one interval? Because it needs two numbers, right? And interval is just utility data type so that you can specify two numbers. Now that data type is in the name rg, so rg.interval. Okay, and the interval constructor functions will take in the lower bounds number and the upper bound, so 0.0 or 1.0, or you could just say 0 and 1, but I usually typed out a decimal number to remind me that this is a decimal range. Okay, now if we run this, because now we have reparameterized the curve, then when we ask for the point at position 0.5, it should be more or less in the middle part of the curve. Okay, so it's more or less in the middle. If I do 0.0, it should be right at the front of the curve. Okay, I can draw a little sphere here just to make it easier to see. So sphere, put a sphere in here. Okay, and 1.0 should give me something at the end. All right. Okay, let's try another value, another functions called point at length. So this one will, you say my curve and point at length and give it a distant value, and it will return a point such that this point will be, let's say, 5 units length starting from the beginning of the curve. So point at length, and if I say 2.5, then it should give me a point that is 2.5 unit from the starting point. Yeah, so roughly 2.5 along the curve, right? So this one is not based on the curve domain, but based on the actual distance, the physical distance. So this one is irrelevant of whether you change the interval to whatever range you want. Okay, and there's many other common operations. So the frame at will. Okay, so I will need a plan here. So let's do O plan. So O frame, but the output is a type of plan. So frame on curve equal to curve dot frame s. So frame s will return a plane object such that the z direction of the plane is tangent to the curve, and then the xy will be perpendicular. So frame s, and this one will take in a curve parameter value, so I will give it at 0.3. Okay, and then I will output O plane equal to frame on curve. Okay, so that will give me that plane here. Okay.
But not depends on the interval.
Yeah.
Depends on the interval.
The
That number 0.3.
0.3.
Independent of the interval.
Yeah, so this is the interval number. So if you look at that, so how do we know that? You look at the documentation. So see, the first input to the frame at is it doesn't pop up right here, annoyingly. So frame at yeah, the first is T called the evaluation parameter or the curve parameter, but whenever you see it called using the name T, it's a curve parameter. That's the convention in mathematics, and also in programming, and also in many software. It's just called T, the T value of the curve. All right, so you have a plan. I said it incorrectly before. So what aligned with the tangent of the curve is the x-axis, which is the red axis here. Right, not the z. So the z is actually perpendicular to the curve. All right, so I say frame on curve. So frame on curve, you expect it to be a plane, right? And then you output it here. Let me hover the mouse over here. It's actually what coming out is two value, not a plane, but also a Boolean value, and then the second one is a plane. Now the plane will be displayed here, and the true value, well, it's just a Boolean value, so it is not displayed on the viewport. Now when you look at that, you have the impression that the output of this one is only one value, right? Actually, it's not. It's output a tuple of two value, true. The first entry in the tuple is the Boolean true, and the second entry is a plane. And when you output a tuple to an output port, Python automatically unpack the tuple into two objects for you. Okay, so why is a tuple? So remember the other day where not the other day, but last week when we learned how to write the functions. Sometimes a function needs to return more than one value. Okay. Now the function point at, for example, it just returns one value, which is the point. There's nothing else it needs to return. The function frame at, it has to return a special Boolean value to tell you whether it was successful in order to find the frame at all, because the frame at sometimes fail. And in order to communicate that information with you, it has to return two information. The first is the Boolean, false or true, And then if it's true, yeah, you can safely look into the second return value and get that frame and do some useful thing with it. But in case it's false, we as a programmer know that okay, that plan that being returned is non-valid or nonsense. You should do the logic differently. You should not use it to draw stuff. So it needs to return two informations. And in order to do that, it needs to package these two informations into a tuple, right? So when you call the function frame add, this line is wrong, so I have to update it. So a boolean and up. Okay. So the function frame add take in a float and return a tuple. Okay. The first entry of the tuple is boolean. Okay, and plan. Right. So if I just for demonstrations, this one frame on curve, I call it frame on curve, but it's misleading. It's actually a tuple. Only the second entry in the tuple is actually the frame on the curve. Okay. Now, if, for example, just let me print out frame on curve, you're gonna see what it means displaying here is a tuple in a moment. Okay, so it's a tuple bracket, round bracket, true, and then the second one is just a text description of the plan object. Okay, and then close bracket. Right. So that's the proof that it's a tuple. All right. So how do I know that this function return a tuple before from a documentation? So if you look at the documentation, so this is thing can look a bit confusing because this is how you have to do some translation from C# language to Python. All right. So in Python we know that it's return a tuple. Now in C#, when a function in C# needs to return more than one value, it doesn't use tuple. In Python we use tuple, but in C# it uses something else. So in C#, by default there's only one return value, which is the boolean, right? And then if a C# functions need to return any additional value, it will do it as an output parameter. So you see this parameter here, it has type plan, and it has this keyword out here. So it's a bit weird. It's a parameter, but it's not act as an input. It's supposed to give out outputs. So that's the weird C# syntax. Okay. When you see this documentation written in the C# language, but you use it in Python, you have to do a bit of mental translation, right? So if you have a C# function that return a boolean and an output parameter, a plan, when you use it in Python, you only supply the first parameter, and then the return value will be a boolean package with the out parameter in a tuple. Okay. There are other functions in C# that has more than one output value, right? A function can return 3 values, for example. In Python, you just package into a tuple of 3 elements. In C#, only the first one will be returned, and the second and the third output will be returned, like return in quotation because it's not really return as an output parameter. Okay, but we're not using C#. We just look at the documentation. So whenever you see output parameter, mentally you just think that all of these parameters will be packaged together with this boolean here, or with the main return type in a big fat tuple. All right. All right. So this is the C#. The closest point taking upon 3D, return a boolean together with an output parameter of type double. When you call it in Python, it becomes a function to take in 1.3D and return a tuple of the boolean, the main return type, and then you take the number, which is double, but in Python the double will be converted to a float. Okay, but imagine this is a 0.3D, then the 0.3D will come at after the main return type. All right. All right, and then after you get a tuple, you have to extract it. So if you want to do if you have a frame, a frame here, again, the frame on curve here is not really a frame, but it's a tuple, right? And if you want to use a frame to draw a circle based on that frame, you need to extract the frame really. So okay, so you use the syntax of the tuple to extract that. And now this whole thing, like frame on curve, square bracket 1, now that is really a plane or a frame, right? If you say 0, then this will be that boolean. Okay, so if I print out only the 0 bit, that will be, guess what, just a boolean value true. All right, so that is some new syntax that we need to learn. All right, let's move on to the surface. All right. So that curve, now there are many functions in the documentation. Now there's no way we can try out all of them, right? But the documentation is there. So one of the assignment in your is today is like to look at documentation and try out, like have a play with those functions, do simple stuff with it, really. All right, so now we move from curve to surface. So you know that a curve is a collection of points, right? And each point has a curve parameter t, right? And the t will run continuously from 0.0 to 1.0. And as t run continuously from 0.0 to 1.0, it will trace out a curve. A parametric surface, I don't know if I have a live demonstrations. I don't think I have a live demonstrations. Okay, a parametric surface is just a 2D version of a curve. Instead of having a value t, you have two value u and v. Now on a plane, if you have two value x and y, it will trace our plane, right? Think of xy and now convert it to uv. So as uv varies, the point will trace, but this time it will trace out a continuous smooth curved surface. Okay, in the previous case we have t. When t vary, it traces out a single curve in 3D. Now you have uv and uv will both vary, right? In a domain, in the limit between 0.0 to 1.0, each of them, it will trace out a surface. All right, and because of that, untrimmed. So if you have a parametric surface, it might curve, but it's always has four boundaries, right? And because if you look at the xy coordinate, it always has like four boundaries, right? And the UV is just a deformed or the curved version of an XY space, right? So it have four boundary, and they have a positive side, negative side. So when you do an XY plane, there's an upside, the up Z axis, and the negative Z, right? Now in the plane, there's also an up and negative, and it's consistent with the UV. Now all of this knowledge is, I think, basic to Rhino curve modeling. This is not even grasshopper stuff. This is just like basic Rhino stuff. But it's important to keep them in mind when working in scripting, you know. All right, so let's create a surface, and then we're gonna reparameterize the surface. So reparameterize the surface is similar to reparameterize a curve. When we take the domain of the surface, now the domain has the two different domains, the u domain and the v domain. We reparameterize it to 0 and 1, and again we can do the point at the frame at and the dot distance at, or the closest point operations on the curve, right? So not sure what is the quickest way to set up a surface. Okay, so I will do a simple loft surface. Let's do a simple curve here. How do I show the gumball? Here, gumball. Draw a free curve, make a little loft. Okay, now I will import it to Grasshopper. And import it to Python as alright, surface. Okay, now important, the input type of this guy gonna be surface, right? So the type in gonna be surface. And then we have two numerical input called IU and IV of type float. Okay. The output's gonna be O geometry. Okay, now let's look at the code. We can copy and paste this in, it's very quick. So first we have to reparameterize the surface, and reparameterize means just set the domain of the U direction and the V direction to 0 and 1. Okay, so we do it similar to the curve, but the way we do it in Python is slightly different from what we did for the curve. So I surface, we invoke the function set domain. This function will take in 2 parameters. The first is either the integer 0 and 1. 0 means it will set a domain for the U direction, and 1 is going to be the V direction. Okay, so 0, and then the second is the actual range or the interval for the new domain. All right. So we're going to do it for the U and the V, and now we can safely say iSurface.point at, okay, and give it 2 domain parameter like IU and IV. Okay, and because now we reparameterize it, we should give it a value between 0.0 and 1.0. Okay, and we'll give a point on the surface. Okay.
Sorry, the first number is the default, right?
The first, let me paste it in first.
That's 0.
So which one? So 0 is the U domain, and this is the
I.
V domain, yeah. Okay, and now we should, as we vary the slider, we should see the point running across the surface. Okay, so this is pretty standard grasshopper operation, but now done in Python. Okay, let's try the closest point function before we move on. Let's try isocurve closest point, and then we move on to like some real example. All of the stuff we've done so far is just like single functions in isolation, just to get a feel of how these data type work, right? And then we're gonna apply it to like generate some simple design pattern on a UV surface. Okay, isocurve. So instead of evaluate a point, let's evaluate an isocurve. So an isocurve is just a collection of points that had the same U or V value. Okay, so if I say iSurface.isocurve, okay, this is a function that take in an integer to specify the direction. So I want to do a U direction, and the other and its value is free. So this will give me a curve which basically a collection of points that has the same U coordinate at 0.3. Okay. So this one should not be called point. This one should be called isocurve, and the output is gonna be isocurve. Yes. All right. So that the U isocurve at value 0.3. Okay. All right, the next functions is kind of useful. The closest point functions. This one will return the UV coordinate. So this one will you start with functions and you call closest point, and it will give it a reference point, and it will try to compute the UV coordinate of the closest point on the surface to that reference point. Okay, so closest point, it take in a reference point, and then the data type for the reference point is point 3D. Obviously, the return value is a tuple of three piece of information. Right, the first piece of information is a Boolean value, true or false, that tell us whether it was successful in actually find the closest point. Sometimes it will return false. Okay, and then you will basically don't do anything else. If it's true, then you can safely look into the second and the third entries of the tuple, and they are floats, so they are just the UV. And then you can put the UV into the point add function or the frame add function to get the actual point 3D for further calculations. All right. So let's put in a reference point. I reference point of type point 3D. Internal review schedule. Okay, so now the output geometry gonna be the point closest to this reference point, right? Okay, so let's change the script a little bit. So ISO curve, so this one, let's delete the ISO curve, let's delete the last two lines. Okay, I'm gonna say, so I surface dot closest point. Okay, I'm gonna give it the reference point, I reference point. Okay, and the output is going to be a tuple, right? So I have to start a tuple somewhere. So I will just create a new variable called tuple. All right, let's put it here. All right. So normally what you do is you need to check out the first entry of the tuple to see whether it's true or false, right? But let's assume this is already true, right? So we only need to extract then the second and the third parameter, and then so tuple dot tuple square bracket 1, that's going to be the u value, okay, and tuple 2, that's going to be what, the v value, right? So we just need to put those two into the point add functions. Okay, so let me close the bracket. So those going to be input to the point add function. So I surface dot point add. All right, this one will give me the closest point, and then I will just send the result to O geometry. Yeah, this is called tuple, not triple. All right, now, yeah, you should see a closest point here, and now let's try to move the reference point, and the closest point should also be changing accordingly. All right. Okay, let's save this file because we will carry on. Okay, save that. All right, now let's build up an example from this. So we've learned a lot of command, but in isolations, right? So now let's generate this pattern. So we're gonna do a bunch of pyramids on a UV surface. Now, of course, this logic can be done in Grasshopper only, but now we're gonna do it in Python, so you know how to use the nested for loop logic. Okay, so let's start with the easy bit. So we're gonna make a little. We're gonna write a Python function. This Python function gonna take in 4 inputs. So the 4 inputs gonna be the type of input gonna be a Rhino plan, right? So for Rhino plan input and the output, I think together with the height value. Do we do the height? Great. Yeah, and the height. Okay, so the input gonna do a function called create pyramid that take in 4 input, the floor plan and a number that represent the height, and then the output is a list of 4 surface. Okay, so a 4 triangular surface. Okay, so let's start. So still keeping the surface UV, we don't need U and V here anymore, but we still need a surface. Let's keep that. All right, so we still keep the reparameterization part. Okay, we're gonna need that later, but now let's define a function called create triangle surface. Okay, so this is a utility function that take in 3 points and return a surface that pass through a triangular surface from those 3 points. And there is no single command in the Rhino command that take in 3 points and return a surface right away. That's why we define a custom function to make it easier for us whenever we want to create a surface from 3 points. You know. All right, so ABC, and remember ABC are assumed to be point 3D. Okay, now we're gonna have to create 3 curves. Okay, and they just happen to be line curve. Okay, so CB gonna be line curve, BA gonna be line curve. Okay, just let me explain, and we can copy and paste in. All right, and then we're gonna create a brep object and then return it. Okay, so rg.brep. Now we haven't done brep yet, right? But it's just another class we're gonna visit more closely. But so brep, and then dot create edge surface. So create edge surface is a static function of the brep data type or the brep class. Now the create edge surface will take in a list of 3 or 4 curves. Okay, and it will try to make a surface between the 3 or 4 closed curve. All right, here we have 3 closed curve. They just happen to be line curve, but remember they are treating curves. So if you look at the documentation of the functions, it expects an I enumerable of curve, and I enumerable is just a fancy name for list, right? It is a list of curve, but as I explained, line curve is also curve. So that's why even though a function asks for a list of curve, you can give it a list of line curve or a list of line curve mixed with notch curve. It's still also fine, right? But here we draw triangles. That's why we just use 3 line curves. All right, this whole function will get you a brep and it will return, so the return keyword should be blue. All right, and then we run these functions for the 3 input point IA, IB, IC. Now we don't have IE, IB, and IC, so let's, for testing, let's just like do RG point 3D and put in some random coordinates just for testing, right? So Control C. Put it in here. Okay, our geometry, and now we remember we don't have IA, IB, and C, so we have to say rg.point3d. That give it some value just for testing. Yeah, I miss it. Okay, now we're gonna do the pyramid. Okay, now we know how to draw a triangle surface. We can use that. We can use that function 4 times. Okay, so this is another example to practice doing functions. Now for testing, we need to have like some for real plane to act as the input for the function, right? So so let's have cone I frame A that has type plane. Okay. I frame B, which type plane, and C and D as well. And for the height, we just hard code in a value, so we don't need an input for height. Frame C. They're on plan, so remember to set the type into plan, guys. For the frames. Frame D. Okay, now we're gonna input in some plan, but here we assume that everything is in a counterclockwise order. So you start from A here and then B, C, and D. Otherwise, you will have a twisted pyramid. All right, so planned. So if you use the planned components, for those of you who are like not familiar with Grasshopper, you do you can specify Grasshopper plans by saying plan. Right, you have a plan component which is empty for now. It doesn't have data. Now you have to right click and set a plan, and then you can right click, choose the origin, direction, tilting for the first plan. Okay. This plan is a bit big, so I will make the display of the plan or the visualization of the plan smaller. Maybe 1. Yeah. Okay. A, B, C, D. All right. Right, and after you're done, save the file. Otherwise, it might take time to reset in case something goes wrong. Do you need a break or should we carry on? Break? Okay. Yeah, let's get back at 11:30. Okay, so 15 minutes break.
from then we go.
Yeah, that's party time. Party time.
Let's do it. Never too early for a party to play that.
You're still warming up to it again as well.
Oh yeah, for sure. Just want to see this one.
I'm having trouble connecting to your.
What's wrong with it?
Bluetooth's a bit funny.
Yeah, mine also speaks. It's kind of funny.
What's that?
Mine also speaks.
Yeah, why she starts talking, she doesn't stop. like it's such a long Bluetooth message.
How's that, Jewel? Or life changing?
It's pretty good.
Yeah.
Pretty nice.
Yeah,
I'm curious
actually-
to see how long it will last.
Yeah.
Like how much nicotine I'll be consuming now.
Do you actually feel like you're smoking less cigs?
Yeah, well I haven't had a cigarette since I got it.
Well,
24 hours. Maybe like 20 hours.
okay. Not too shabby.
Yeah. We'll see. Long term play. Definitely like happy I got it. I mean, since
Oh,
I got
yeah.
the last one. I'm curious to see.
Do you get the nicotine rush?
Happy to be like I was sitting down like a rock climb on the walk to had a little bit of that, but
Yeah, even yesterday when I tried that, it was like a
Yeah.
pretty severe rush.
yeah,
Nice.
Yeah,
Because I mean, I don't smoke that much, so
exactly.
whenever I get the nicotine in, it's like,
Like it's quite delicious, like a hot life.
yeah, I dig it though.
This must be pretty concentrated.
Oh, the jewels? Yeah, of course. I mean, you see how tiny that pot is.
Yeah.
I mean, like, per volume, you say like at least 30% of that is nicotine.
Yeah, yeah. For sure. I mean, much better. Much better. Much appreciated.
Have you been going to craft a lot?
Yeah.
Nice. I'd be down to check it out this weekend. Something actually here. Yeah, I'm so down on things. But it's crazy how like all the weddings and all like things that I had to attend happened to me in the same like 3 weeks span. But yeah, but it works. It works because there was like the first 3 weeks of school, so we were paying.
Hey.
Yeah, imagine like but I think it was around
So.
yeah, I should probably get on like looking something for that holiday earlier than cheaper. It's like 3 weeks. Yeah, of course. Whenever you're like planning on it, I'll sit down with you and I'll give you For New Year's, I'm usually there. When I'm in Morocco,
Yeah.
see, I'm going back to work and all that.
As far as
But it's usually like all the people from Casablanca go to Marrakesh for like between after Christmas and then that's why I'm going to party. Yeah. And you have like tons of fun stuff. Okay.
that seems like it would be slightly.
Yeah, but I mean you can
Still have fun. Yeah. You say Marrakesh is still like a place to like hang out and that's
for sure.
the whole.
It depends on how long you're there. I mean, if you're there for like a week, then I wouldn't tell you to spend the whole week in there. You like spend 2 or 3 days and then go somewhere else. So there's a city that's very, very cool. It's about, I'd say 2 hours in Marrakesh, called Essaouira. Essaouira. So it's basically an old port town. So you have like the old city that's all old pedestrian, like small like little pathways in between, but it's on the beach.
Okay.
Yeah. Yeah.
It's not like super cool. That's in like industrial type.
No, like yeah, like fishing.
Nice. It's a weird.
Yeah. So like,
And there is a festival as well, right?
Yep.
Music festival.
Yeah, it happened like maybe a month ago or something.
No.
Yeah, my friend. And there's one in Marrakesh too that happened to be Oasis.
It was, I don't know.
Yeah.
But it was I really wanted to go to that festival.
Yeah.
But
It's cool. Yeah. I mean, they keep like every year more and more festivals to pop up in Morocco, and they're doing well.
Yes, good business. I've been 2 times
Really?
in Morocco, yeah.
What part?
Marrakesh, the first time, and then I drive from Italy and Spain to Hungary,
Yeah.
and then all the part, the northern part, the Atlantic, the mountain.
Oh, nice.
That's
Oh,
fantastic.
nice. That's
Yeah,
great.
I've been to the desert. It was a long time ago, I could remember very
The
well.
desert is really far, like all the way to Sierra. It's like super south, like the most southern part of the country.
Sugar.
So you're talking like maybe an 8-hour drive from Casablanca.
Pretty great. You know what is the thing up all the like, yeah, I don't think we'd like a lot of
But next year I will be done because it's like
Hoy llegó una carta de la compañía de internet, pero no la pudimos ver. Debe estar por ahí.
But
Su internet
it's only
está
like 3 days when you
bloqueando a nuestra puerta y nosotros no le estamos abriendo.
3 hours away.
Pero
Yeah.
pronto lo vamos a
And
hacer.
it's cool. They do a good job every year. It gets better every year. That's more American.
Hey, ¿sabes qué? No sé por qué me tira error. O sea, lo hice todo perfecto como lo decía 8 veces. Me dice como que expect y no, como que los points, hay algo con los points. Vamos a ver.
Dos point redeem. Point redeem. La línea está curve. Control point. Porque tienes un punto solo, parece.
But no.
Points. Great control point queen. 5 points, 5. Great control point queen.
since the first line, desde la primera línea me quiere dar entonces, ¿qué era? ¿Ahí?
All right, so then. Alright, so before the break, we wrote a function that create a triangular surface from 3 points. Now we have to build a pyramid from that. Now the code is straightforward, but it's a bit tedious to type out. So let's do copy and paste, right? So as long as you, alright, so just underneath the create triangle surface definitions or functions, we define another function called create component surface. By component, I mean the pyramids, but then we use this pyramid to populate the surface, the big UV surface. That's why we call this component. Okay, so this function is going to take in 4 plane, the 4 input plane that we, for testing, we're going to use the one that we input from that we receive from Grasshopper Canvas. So 4 planes and a double. Alright, and the output gonna be a list of 4 triangular surfaces. Okay, so yeah, so we have A, B, and C and D, and these are plane, right? So we can say dot origin. The dot origin property will give us the point 3D, that is the origin of the plane. So we know the 4 bottom points of the pyramid already. Now we need to compute the top part of the pyramid. So in order to compute it, the top points. Now this is not a standard pyramid, right? The pyramids depends on the orientation of the plane. The reason why we want to have the pyramid have an adaptive orientation to these planes is because later on we're gonna the planes will come from the UV surface, right? And as the UV surface curve up and down, we're gonna get a bunch of planes lining up along the surface. And if we use those surfaces to influence or to compute the orientations of the pyramids, then the orientation of the pyramid will kind of flow influence, but also like kind of flow along the UV surface nicely. Okay.
Are we recording?
It's still recording. I didn't turn it off at all. Okay, double check. All right, so how do so okay, we know the 4 corner points from the 4 input planes, right? We just need to know now. We need to compute this point, right? And if we need this point, then we just call the create triangular surface 4 times and give them like the respective set of point 3D, and then we have 4 surfaces coming out. That's fine. Okay, so to get this point, we're gonna first compute the average of the 4 corner. Okay, we know the 4 corner. We can compute the average by just add them up and divide by 4. Then we should arrive somewhere in the center, more or less. All right, and then we need a direction to go from the center, and that direction is just the average z directions of the 4 planes. So we take the 4z vector. Okay, so if you have a plane, you have to say dot z axis. You will get the vector 3D that represent the z axis of those plane objects or plane inputs. And then we add those up, and then we divide by 4, and we unitize it. Well, actually, we don't need to divide by 4. We just need to unitize. We add 4 vectors up, and unitize to 1, so it had length 1, right? All right. So we have a point here, and then we have an average vector that points in the average direction of the 4 that has length 1. All right. And so from that point, we walk along the directions of that average z vector a distance that's equal to the highest input. Okay, so remember highest is the input to the functions. All right, and then we will arrive this point. Okay, so that's how we arrive this point parametrically. So this is what the codes look like. So first we compute the average z vector. Okay. So we take the z-axis, the z-axis of each of the frame, add them up, right? And we got the sum vector. And then we have to unitize it, so it has length 1, right? So once it's unitized, if we multiply it by a number, it will scale to the right length right away. So, you know, unitize a unit vector is easy to work with. Okay, so if you have a vector 3D, so a vector 3D has a function called dot unitize. Again, look at the documentation. But this one is, this case is obviously what it does, right? You don't even need to look at the documentations. All right, so now that is the average direction. Now we need to get the center bottom, which is the average of the 4 origin of the plane, right? So frame A origin, which is a point 3D, plus another point 3D, and then divide by 4, okay? So everything divided by 4, or equivalently multiplied by 0.25. All right, so form the point 3D, which is the center, and if I add a vector, so the height vector, the z vector, but before I add, I scale the z vector by height, right? So it's a long vector, right? And I add it to the bottom. So again, in random common, when you add a vector to a point 3D, you get a new point 3D at the tip of that vector, okay? So basically, you offset a point by a vector, and that will give me the top of the pyramid. All right, now it's just a matter of drawing the triangular surface. So we call the create triangular surface, but this time we give is the origin of frame A, so corner A, corner B, the top point. That's one of the surface, and then okay, we just rotate it around and get the fourth surface. So I hope everything is clear, but we're gonna copy and paste. We're gonna kind of tedious to type in. All right, so we have 4 surface, and we store them in 4 temporary variable, and then we just package them into a list, and then we return that list. Okay, and now we need to invoke that function just to test if this function runs correctly. So we're gonna invoke the function, give it the 4 input frames, so I frames A, I frame B. The height is gonna be 3.0. We hard coded it, and then we're gonna put the geometry. So I copy only this bit, the triangular surface. We already have it defined, so we copy this bit only. Control C. Okay, we should see a pyramid coming out, and if we change the input plane, the pyramid should also change.
Question. Why isn't the word z-axis or origin in blue?
Because there's a property, not function, only functions in blue. Yeah. And that's depend on the code editor. Some code editor allow you to customize the color scheme. So in C#, I often like to color the property as a different color as well. Okay, so we got one pyramid. Now we need to populate it over the surface, right? So I think I should split it into steps. First, generate a grid on the UV and then populate it. So let's go back to Grasshopper. We need to modify the input a little bit. So now we have this input. Let's call it IU divisions, because specify like how much we want to divide the surface in the U surface. Okay, IU division, and it's going to be the integer, not a float anymore. So, and this is IV division. Divisions. Okay, and the range should be changed to like from 1 to 20 or something. The range of the slider should be changed from 1 to 20. Okay, now I'm gonna expand the code again. The code is a bit tedious to type in manually, so we can copy and paste. But let me expand first. Okay, so we have two functions that we defined earlier on, and then we those two lines of code we already have, right? So we just like reparameterize the surface. So now if you have a UV surface with 4 boundaries and everything reparameterized, so in this corner you have 0, 0. In the upper corner you have 1, 1, and this is 1, 0, and 0, 1. It's just the coordinate, right? So from those coordinates you can use a for loop to like divide them into a grid of points. Now we already know how to do a grid of points on the XY space, right? Now we're gonna do a grid of 2D points, but along the UV space, right? So we're gonna have a for loop. The math is just slightly different, right? But here's how we do it. Okay, so this is just an empty list I created first. So this list will store all of the triangular that make up all of my pyramid. So it's empty at first, and I'm gonna populate it in. All right, so we have a for loop. So for I in range of 0 to U division, right? It's just like when we do the XY. So we have an I and J loop that go from 0 to the number of column or number of rows that we want. All right. Now we want to evaluate a frame or a plane at a grid, a UV grid points, right? So if we add column I and row J, then if we divide it, it's going to be I divided by IU divisions, and then J divided by. So remember, I will go from 0 to IU division minus 1, right? So this whole thing will go from 0.0 and then equally spaced up until 0.9 something, almost 1, right? We're not getting to 1 yet because we're gonna draw a pyramid, so we're gonna add one later on. So same for J. So this is just like the logic of spacing equally from 0.0 to almost 1.0. Okay, so this is the U coordinate. This is the V coordinate. We put it in the frame add function. The frame add function, we remember, returned a tuple of a boolean and the actual plane. So we're gonna take the plane out. We assume that the boolean is always true. We assume that the frame add operation is always correct, always successful. So we just safely read out. Remember, so this big fat thing return a tuple, and then we have the tiny square bracket operator at the end. Okay, that's one frame. So the frame A is here, and then frame B gonna be the neighbor one, right? So it's just basically the neighbor one. We just add 1 to it to get the neighbor grid, right? Okay, so J plus 1. So we go in the counterclockwise. So this logic we see before. So but this time we work in the range of 0.0 to 1.0 rather than from 0 to an arbitrary range. Okay, that's all the difference. All right, frame A, B, C, and D, and then with these 4 frames we can build the pyramid. So create component surface, take in this frame, and we put in the fixed height for now, the fixed height value. This will return a list of 4 triangular surface, right? And we're gonna append this list or extend. Well, this is the final result. Let's store all everything, right? So all surface dot extend, and we give it the 4 surface of this particular pyramid. All right. So each time this run, we have a new pyramid that consists of 4 surface, okay, and we let it run for I times and j times, and we have everything. So I hope everything is sufficiently clear. So the thing with Python is that you can only test the results at the end, right? So when you write a lot of code and then you run it at the end and you get an error message, it's kind of hard to understand if something go wrong. So normally when you write a piece of Python code, you kind of have a way to test the intermediate result. But here in this example, I kind of do a lot of things going on, and because I have debugged it and make sure that it's run correctly. So you just need to copy and paste, you see the result. But in real life, you have to break down into smaller steps in order to test the result, right? All right, so let's copy this part in. So the part from own surfaces, okay, and we add it. Alright, we're gonna add it just under here, so delete the old geometry line. Okay, my division is 1, that's why I have only 1 pyramid, but I can have more here. Okay, so normally imagine you replicate this logic in Grasshopper. So normally you generate the frame first, right? And you should see the frame being displayed correctly in the Rhino viewport before you carry on to creating the pyramid. But here, like, we create the frame, but the frame lives inside a Python script. It was never being output, so you don't see the results. So that is why if something goes wrong, it might be hard to debug, right? So that's why I built this example by doing the create triangle surface first, test to see if it's working correctly, and do the component surface function, and then immediately test it. And after I test and know it's run correctly, I remove the testing part and then write a for loop. Okay, but here even if I do that, I still don't see the grid of pawn 3D and the frame on the UV grid being generated. But of course, for me, I've done this logic so many times, so I'm kind of confident that I can write this short piece of script in one go without much of error. Or even if there's an error, I know I can find it easily. But like for most of you, you're gonna make a lot of mistakes along the way. You're gonna see a lot of error message that it's not that's not clear, especially the index out of range error is one of the most annoying. Alright, if you happen to use Rhino 6, you can run everything into the preview component and turn on the render mode. And Rhino 6 had a really nice shading with ambient, real-time ambient occlusion shadows, so to make it the geometry much more stand out. Okay, now the next bit is not in the slides. Now let's try to replicate the logic of attractor patterns in Python. Okay, so as you know, in parametric design, the attractor technique is one of the most kind of commonly used, especially in the early day of Grasshopper 2012 and 13. Everybody who learned Grasshopper at first like try to do some attractive pattern because it's kind of easy, intuitive, and it has an interactive result. Okay, so now we're gonna do it. It's so popular, it's getting a bit cheesy. So, but we can replicate the logic here just to show you how those interact with the for loops. We're gonna use an attractor pattern. By the way, raise your hand if you don't know what I mean by an attractor pattern in parametric design. Okay. A few. Okay, so let me summarize in 2 sentences before I move on and you can see it. So attractor pattern is where you have a collection of similar looking items, but you want to vary a certain parameter, for example, the height. Okay, let's vary the height based on how far each of the component is from a common reference point. So we have a reference point, right? And we use a reference point to somehow influence the height parameter of each of the pyramid. And because each pyramid has a different distance to that reference point, they will have different heights, but they vary continuously. So the height is kind of increasing. So the distance between the reference point to the pyramid is kind of increasing slowly. So the heights can also be increasing kind of in a continuous manner. All right, we have a reference point here. So normally we call it the attractor points on the attractor, but here we already call it reference points. Okay, so very easy to implement now. Now the height is 1.5, right? So here, rather than use 1.5, let's compute. This should be a formula that depends on the distance between the reference point and, let's say, frame A dot origin. Okay, so we assume that we measure the distance from reference to, instead of the center of the pyramid, let's just pick the A corner of the pyramid. All right, so distance to refer. So I'm gonna have 2 empty lines here. All right, so here now the height is 1.5, right? So let's, instead of making it 1.5, let's make it height, okay? Which is just a variable. So now I have to define height. So height is equal to something, okay? Now height is going to depend on the distance between the reference point and frame A dot origin, right? So I need to compute the distance first. So distance equals to frame A dot origin dot distance to I reference point. Okay, so nothing surprising there. Okay, now the height is going to depend on the distance. So here we're going to have a kind of a magical, fancy mathematical formula that has the word distance in it. Okay. All right, so, the easiest one to do for attractor pattern is just to make it shorter as distance, to make the height larger as distance get closer. So how about 3.0, just 3 divided by distance plus 1. So when distance is 0, the height is 3, and as distance get larger, the height will go down. I might need to scale distance by a factor by 2.0 or whatever, but we can try it later. Okay, so let's run this and then move the reference point around and see if things update. Let me fix the error, 0.3D. Missing. Okay, everything is really flat. So let's move it this. Okay, so I'm gonna scale it up a little bit. So 3 is small. Let's make it 20. Yeah, okay. Yeah, the closer they are to the attractor point, the higher it is. All right. Okay, we are doing good with time. All right. Now let's save this here. I will give you 10 minutes to try out the following thing. Instead of using a point attractor, use a curve attractor instead. All right. So you know how to compute. We haven't learned how to compute the closest point from a curve, right? But I think it's on one of the slides and in the documentation. So let's try to look it up. So let's, instead of input a reference curve, right? All right. And then for each pyramid, so inside the logic here, compute the closest distance between, let's say, frame A, not origin, to that curve, and then use that distance to do the. All right. So I would say I reference curve. And I will make a simple interpolation curve from 3 points. Today, Tuesday, you have studio class, right? What time does it start? 2. 2, right? Okay. So we're gonna finish the standard hours like 12:15. So. Okay, curve go into here. Don't forget to set this to curve. The input. I'm gonna save this one online as well. Just something to keep in mind: the closest point function, when you call on a curve, it returns a tuple, not directly. It does not return the closest point right away. So be careful. Yeah. Okay, so I will do it. So let's try to do it yourself, and then I will show the solutions in 5 minutes. So as you see, there's no direct function to compute the distance between a curve and a point. That's why you need to find the closest point on the curve first, and then compute the distance between those 2 points, and use that distance to compute the attractor math. So. All right, so here is the solutions. So from the code, we call the closest point and give it the frame A origin, right? So this will give us a tuple, and the first and the second entry, which has index 1. So the second entry in the tuple will give us the t value of that closest point. So it's not a point, it doesn't return the closest point directly, which is the t value of that point, like the curve parameter value. And from that, we have to put it in the point function to get the actual point 3D, right? And from there, we can measure the distance to the origin, to frame A origin. All right, here I just scale the map a little bit. Okay, you need more time, or shall I carry on? More time? Okay.
Okay,
Yeah.
distance for like why is the plus one for height is
Which
equal
one?
to 40? No, 2 lines down. Yeah, the last one. Why is it?
The plus 1.
Yeah.
If you don't have plus 1, you accidentally have distance equal to 0. You have a division by 0, which gives you an error. So this is just a small
Just
trick
be sure
to.
that
Yeah. You will still get some decent result without this, you know. Yeah, it's still good result, but this is like a safeguard. Yeah, without this one, the closer you are, the faster it will shoot up to infinity actually. And so you see, like it spike out very quickly, right? So one will make the spike less dramatic. Okay, still need more time or? Alright, so. Okay, so we can move to BREP. So BREP is even a bigger topic, but we just touch on a few common basic concepts so that you can, just good enough so that you can look at the documentation yourself. So surface is the main kind of working object in the Rhino, software. It's enough surface, but for convenience, surface is grouped into BREPs. So BREP is called boundary representation, but each BREP object, or if you have a Python object of type BREP, it's basically just a collection of surface. Each surface can be optionally trimmed. Okay, so the surface object that we do is always a 9 UV surface with 4 boundaries. Okay, now the triangular it has 3 boundary, but that is because the fourth boundary has length 0, but it's actually have 4 boundary. Okay, if you want to have a hexagonal, it's not possible directly using one single surface in Rhino. You have to trim it in order to get the 5th edge. Okay, so that's where we need BREP. So surface is the basic UV. So the underlying, so in computer graphics, the underlying freeform surface is always a UV surface with 4 boundaries, right? But then depending on how you trim and you combine it together, and you can model an object or anything, right? The surface is the basic thing, but BREP is like a more higher level things to work with. So BREP is a data type in Python Common as well. When you import stuff, you can have a BREP somewhere, and you can read it into a Python script using the type in BREP, okay? And then you can access, and if you start in a variable called myBREP, then you can say myBREP dot, and you can access all of the functions and property of that. Again, you have to look at the documentation. BREP, has a very large collections of properties and methods. So now I will tell you briefly what properties that BREP has, like the basic one, the most important one, and then how do you create a BREP from scratch? So let's assume that we already have a BREP from the Grasshopper canvas, and we just read it in Python, and we just query or extracting the property of the already existing BREP, right? And then I would show you various ways to generate BREP from Python itself using profile, curve, or points. So if you have a BREP object store in myBREP, so because BREP is made up of surface, then you can say dot surfaces. So surfaces is a property, and the data type for this property is a list of elements, and each element has data type surface that we have been working on. Okay, and each surface has the point add and the dot frame add functions that we've been doing. So if you read something in as a BREP, you cannot say myBREP dot frame add directly, because a BREP doesn't have frame add upon it. You have to retrieve the specific surface inside the BREP. Now, even if the BREP have only one surface, you still have to go into the surface list and return that only surface before you can do the BREP. You can do the point add and the frame add operation or the closest point operation. All right. BREP also have their closest point operation that automatically act on all of the surface automatically. But for example, frame add and normal add or tangent add, for example, are related specifically to the surface. If you look at the documentation for the BREP class, you don't see any dot tangent add, okay, or a dot frame add or a point add, even though there's a dot closest points. All right. This one will return a number. So this is a list data type, right? And a list data type in C# or Python. Well, here this is actually C# list, but we call it from Python. So any C# list has a dot count property that represent how many elements in the list. You can also say length surface using the Python syntax. That will give you the same thing, but this is a C# list, so we use the C# style of querying the length. All right. Retrieve. Okay, so that is the count, and then if you have a surface, right? So most of the time you will start with a BREP that has only one surface. So if you draw a left surface, you read it in as a BREP to Grasshopper, that will give you a BREP of one surface, and then you can safely read out the surface as index 0, right? If a BREP does not contain anything, you get an out of range index, obviously, but here we know that it has 0. Okay, and that's how you retrieve a surface. And what you can do with surface, well, we have done a bunch of things with surface, so now you know what to do with those surface, right? You can trim the surface. So again, look at the Rhino common documentation, which I will do it in next minute. Actually, yeah, let's do that. So Rhino common BREP. class. So again, here we haven't talked about how to create a bref using Python. We just say that we already have an existing bref, and we just say bref, my bref, the variable name, and dot, and then, okay, these are all of the trimming curve properties. And edge curve. We have the closest point. Do we have closest point? Great, so this L. There should be closest point. L. I'll just search for that. Yeah, closest point. This is a more fancy closest point that tell you whether its closest point rely on the boundary of the trimming edge of the trimming. And there's a trim method, let's say. So if you have an existing bref, and if you call add trim edge or something, or add trim curve, yeah, and then it will use this curve to trim the edge. All right, so we won't have time to go through in all of this, obviously. Or they also split, which is useful to split a bref with another bref. Split bref double, and then there's tolerance. Transform is just to transform, rotate, or the transform is just like transform the whole bref in a solid manner, just like it's a rigid object. So actually, all of the 3D object, geometry object has to transform, not just bref. Okay, so now you notice there are a bunch of static functions here. Now these static functions are here to assist to create a bref from scratch, right? Just like in the curve class, there's a bunch of static functions that help us to create the curve from scratch, like curve dot create interpolate curve, and curve dot create control point. So here there's a bunch of static functions. So you invoke this function from the data type name or the class name, which is capital bref, like bref dot, and then create from. So probably one of the most useful one is bref create from loft. I have it on the slide. That's C# syntax, so it's kind of hard to look at. Okay, so rg bref dot create from loft. It takes in a list of curves objects, so line curve or NURBS curve or just generic curve in general. The next two parameters is kind of weird because when you create a loft using the standard Rhino graphical user interface, they never ask you for these two parameters. They in the documentation they say the starting point and the ending point of the loft. I'm not really sure what it means. The documentation does not make it clear, and in the Rhino main user interface, when you create a loft, it doesn't ask you for this information. So, but the documentation also say that if you don't need to use them, just put in this special value unset point 3D. Okay, so I always put that because I really don't know what useful it is. All right, so just put it there. The next parameter is intuitive. It's just a loft type from normal type. So these are the value predefined in this data type. So loft type is a special data type that has 5 possible values. It's just like Boolean is a special value data type that has only two values, true or false. So this is a Rhino enumeration data type. So enumeration is a kind of data type that have a finite number of possible value, right? So it's normal, type, loosen, or whatever. The final one is a Boolean value that tell whether you want to have the loft to loft back to the beginning to the first profile curve to form a closed loft or not. Okay, so if you say false, then we just go from the first loft on to the middle and stop at the last loft, the last profile curve. But if you say true, it will loft back to the first one. So this is how you create a bref from scratch. So the whole thing. So this command. It's a create from loft, but what it gives you back the return values of these functions is not a single bref. It's actually a list of brefs. That's why I started in a variable called brefs. Okay. Now most of the time, this list of brefs has only one bref anyway, but sometimes depends on the profile curve you give it. It will give you more than one bref. For example, if you give it a width profile, little profile curve, which is like a polyline, right, or poly curve, Rhino will decide that, okay, I will give you multiple brefs as a result, right? But if you give it a bunch of like very nice list of NURBS smooth curve, then this list will has only one brefs, okay? So here in the next line, pretend that I already know that there's only one bref in this list. I just read out the first one safely without worry about out of index error. You know, sometimes if the bref, sometimes this command can fail. right? If you give it two profile curves that's like coincide with each other, I think this command might fail. I don't know. I haven't tried it yet. In that case, this list is either an empty object, so it's not even a list, or it's a list but with no elements, right? So you might have to be careful in that case. But here, if assume that the curve, the profile curve is nice, you will get a nice brep coming out. All right, so you get a brep, and again, a brep has a surface object, and I assume that again, this particular brep has only one surface, and so I read out the 0 surface right away, okay, and I start in a variable called my loft surface, and then I can do all of the normal operation on it. Yeah, so creating a loft in Python script is a little bit indirect. You create it in a brep. It gives you a list of brep. You take the first one and then get the surface, list of surface, and then take the first element, because that is the most generic way that how random command works. But if you know that okay, it's only one surface, then you just read out the first brep and the first surface from that breps. Okay, so this is there is many methods that you can try at home. So now let's talk about the assignment. Assignment is similar to last week. It consists of a small problem solving, and then an open-end design, and then some experiments. Assignment 4. So task 1, okay, again, this is a simple exercise to practice with list and for loop. So we take an input curve, okay, and then I want you to divide this curve using a for loop. Actually, there's a function to divide a curve into a list built in random common, so you don't even need to use a for loop for that. But you know, I encourage you to use the for loop, like, and then to evaluate a series of points along this curve, and then connect these points together into a list of lines, right, and return that line. Okay, so just a small problem solving to practice with some curve, some list, and some for loop logic. Okay. And of course, the curve is not reparameterized yet, so you can reparameterize inside the script, or you can cheat by doing it right here. If you do it here, then you don't have to do it inside the script anymore. Okay, to make the math easier to work with, you know. All right, so this is small problem solving. Now, task 2 is optional. Was optional, but you should do it. It's optional in the sense that there's no way I can grade it or like judge like whether you finish it or not, because it's like more like an open end. You should look at a random common for brep surface and curve, and look at all of the interesting functions and try it out, writing like a 1 or 2 line Python script to try it out and get a feel of it, okay? Because there's no time in class to try on all of this functionality. Like I also learned this why I, you know, in my everyday work, and I look it up when I need to. It's not like I have a 24-hour course where I learn everything in a bootcamp manner. It's not like that. Most programmers, you know, they know the basics, and then they always have the reference next to them whenever they do any software or any programming library, okay? And later on, when you used to this kind of looking up a programming library, then during all the courses on even the studio, when you need to look up a Python or a C# company for a robotic library or for a pathfinding library, you should have you should feel more comfortable looking at documentation. Now, of course, only like big API from official company usually come with this nice documentation. Script written by a random individual or share online usually don't have documentation. So that's another story, okay? But and if you're familiar with the documentation of a C# library and tried it out, then many of the software on the Windows for the Windows operating system these days are written in the C# language as well, even though you can use it from Python. So Revit API, which is the Revit equivalent of random common, is also, let's say, is also written in C#. Same for Dynamo. FreeSMax and Maya used to be C++ only, but now they also support C#. And the documentations, of course, the name of the class, the functionality is different, but the way it is structured is the same. It's just a collection of class, and each class has subclass. Each class has a method. Each class has a list of functions, properties, static functions. Okay, so they're kind of similar in the sense. So, this will be useful not just for Rhino, but many other things. Not every software have a C# or .NET library, though. The SketchUp is a good example where it's a different kind of language because it's meant to be cross-platform. Okay, so if you want to look up for specific challenge to do a task to this is a possible challenge or exercise. Use color to visualize the curvature value. So if you have a surface, Rhino Common allow you to query the curvature at a specific UV point, right? But this curvature, if you look at it, it's just not a single number because curvature is 2 or 3 different number, and there's different type of curvature, Gaussian curvature and other kind of curvature. And Rhino support a few. Okay, so look at the Rhino Common documentation to see how you extract these. And then for each of the curvature value, convert it to a colors and then visualize it. Okay, so generate a grid of UV points for each of the UV. Look up the curvature, visualize it. Of course, I know you can do it in Grasshopper only, but it's a good practice to do it in Python. All right. Then try to do some trimming, prep trimming. Actually, prep trimming is always a tedious thing because. So I do prep trimming from Python. All right, and this is an open exercise. So similar to last week where you come up with an interesting geometric design, but this time you're supposed to use curve, prep, and surfaces. All right, and with some color as well if you want to. You are not required to render this, but if you think this look nice, you can render them, or at least if you use Rhino 6, take a screenshot. I ran a screenshot and also put it in your submission folder. If there's something image nice, I will ask you if you want to share it on social media on the ICD and iTech website as well. Okay, so if you're confident that you come up with something nice, make sure that you share it with me so that I can share it on social media. All right, any questions? Oh, I think we're running a bit, 10 minutes over time, sorry. Okay. All right.